Anytime you have multiple threads or processes that share memory, you run into a possible problem where the processes or threads can manipulate the memory in such a way that it breaks one of the other threads or processes. For instance, take a look at the method I have defined on the screen already. Notice it's simply accepting a variable x, assigning x equals x plus 1, and then printing x. It looks really basic, but what's going on behind the scenes, you have to realize there are three statements going on here, or three operations. One is retrieving x and adding 1 to it. The second one is assigning that result back to the x variable, and the third one is printing it. Technically, the x plus 1 is two separate things as well, but let's just assume that's one operation. So we have three things happening, and let's say test is a process method where we have 10 different processes all executing test at the same time. We wouldn't necessarily know, especially if x is a shared variable, we wouldn't know if x is safe between the three operations. In other words, if we enter this thread where x is 3, then we would expect it to be 4 in this statement and we'd print 4. But if all of them start at the same time and possibly one is 3 and then one starts again and it's already incremented x to 4, that could mess things up because now x might be 5, and then that was an unexpected result because these are all happening at the same time. Okay, if it sounds confusing, it really is a confusing situation. It's sometimes referred to as a race condition, where you don't know if this thread is going to finish all of its statements in time before another thread operates on the same memory. So to prevent problems like this from happening, we have a construct called a lock. Now, a lock is pretty much an all or nothing proposition. When you acquire a lock, you are the only thread that should have access to what's behind that lock. And until you release that lock, no one else should be doing anything behind that lock as well. So everything else should be in a wait state. So if we were to wrap this entire set of statements in a lock, we theoretically then could prevent any harm from happening based on x changing between these two statements. Now, this is a really simplified example here. The one I'm going to do now is actually a little more involved, and it really demonstrates how this can be a problem in the real world. So first, I'm going to put all the import statements I need in here. The new one that we're looking at here is lock, and that is what command we're going to use to protect our data. But we're not going to be able to protect it first. We're going to actually write unprotected code and see what happens. So I'm going to define my main process to call this test list manager no lock. So let's define what that actually is. This test list manager no lock is going to create a new manager, and from that manager we're going to create a list. So we're going to have a managed list, and then to this list I'm going to append the number 1 twice. Now we're going to calculate using processes the Fibonacci sequence, or at least we hope we're going to. Let's see what happens. So we'll create our jobs much in the same manner we've been doing it in all of our demos. And here we have jobs is equal to this comprehension of process objects, and we're going to create a list worker no lock method. So let's go ahead and put that in now. We know we need it, and let's put a pass for now. And we're just going to pass to it the shared list, so our managed list, and we're going to create 10 of them. So hopefully we'll create the first 12 numbers in the Fibonacci sequence, because we're starting with the 1 and the 1. And if you recall, the Fibonacci sequence is the next value in the list is the sum of the previous two. So the next one will be a 2. So it'll be 1, 1, 2. Then the next one should be a 3, because 2 plus 1 is 3. The next one should be a 5, because 2 plus 3 is 5, etc., down the list. Okay, so that'll be our worker. Everything looks good. So let's go ahead, and in this worker, we are going to obviously have to contrive some stuff. If I were to do this without sleep statements, we would have race conditions where we don't know if we're going to get the result we want. We could play with that as well just to see what happens. But let's go ahead and do a debug statement, and we're going to say we're starting. We may turn that off later just because it could get noisy. And then end, so we'll know the process has started and ended. Then we're going to get the first value, so we'll call it val1, and we'll set that equal to the list, which we are, by the way, passing to this method, the list, and then we have to get the second previous, or second to last value in the list. To do that, we have to say len of the list minus 2. And then we're going to, before we get the second one, which will be length of the list minus 1, let's really make this interesting by sleeping a random number of seconds. And then we will append to this list the sum of val1 and val2. And once we have that assembled, we should be able to see the Fibonacci sequence, except for the sleep in here and the fact that we're running in a process. What could be the problem? Well, let's take a look at this. When we start this, we get the value that's the second index from the right. That in itself is not a problem. That looks pretty clean. But then we sleep, and then we get the value that's the last value in the list. What's the issue here? Well, some of the other processes may have altered L in the time we were sleeping. So this len minus one, length of L minus 1 might yield a different result than it used to be. Let's say we start this and list is 1 and 1. And let's say in the time we're sleeping, the 2, the 3, and the 5 have been added. Now we're going to get a 1 and a 6, or 1 and a 5, which will make a 6. That's a problem, because now we are not, 6 is nowhere in the Fibonacci sequence. Okay? Let's just see what happens. So we'll save this, and we'll bring up a terminal. And we will start Python with locks demo. Okay, all of them have started. They're ending now. Notice they're ending at different times. Well, that's interesting. 1, 1, 2, 3, 4, 5, 6. We have nothing close to the Fibonacci sequence. They are all sequential. But that's because, if you think about it, when the first one is acquired, basically all these threads start and they get the first value. The first value is always going to be 1. Then when it's their turn to operate, it really depends on what the previous value or the last index in the list is. In this case, if it's a 5, it becomes a 6. If it's a 9, it becomes a 10. So all we end up doing is getting a list of contiguous values, and it's not the Fibonacci sequence. Let's get rid of the sleep, just out of curiosity, and see how this performs. Actually, it performed a lot better because of the fact that these are running relatively atomically as far as getting the value and then getting the second value. So we are actually getting essentially the Fibonacci sequence. But what did that depend on? It depended on us not having any delay between calculating value 1 and value 2. Is that always the case? We can't guarantee that. Even if we did a sleep instead of random, we slept for 1. Oops, did I? Oh, not ran in, just sleep 1. Okay, let's try that again. Okay, we end up just getting the sequential list again. So if there's any delay between calculating value 1 and value 2, that could be problematic. Okay, and another way we could demonstrate that is if we were to say for I in range rand int 10,000 and some other number. And then we could just, we don't want to print it, that could be a problem. We can just say j equals I. Okay, it's a really lame statement, but hopefully I'm going to suck up some CPU cycles here. Now, it wasn't enough to cause that much grief, but it did enough here. So we did 1 and 1 is 2, 2 and 3 is 5, 5 and 3 is definitely not 6. So we had one goof up in here, and that threw off everything else down the chain. Okay? So what this is telling me is that whatever I end up doing here, I have to do in an atomic operation. Atomic means all or nothing, or all together at once. So I'm going to return the code by undoing here back to the random sleep. Okay, so that we're back to where we were. Let's save it. Let's use a lock. Okay, so we're going to need, instead of test list manager no lock, we'll say test list manager lock. We'll need that method. I'm going to actually copy the other method here because it's essentially the same thing we're going to be doing. I just need to crank this over to the left a little bit and get rid of the no. Then within this one, I have to create, besides the manager, I have to create the lock. Okay, and it's just going to be a lock variable. I don't have to do anything with it in this method except pass it as a parameter or an argument. And I need a new worker, so it'll be list worker lock. Okay? And we will create it right here. And it'll be L and lock. And I'm going to copy everything that's in this method to paste over here, because it's essentially going to be the same code. The biggest difference is, however, at the beginning of the method, I am going to acquire the lock. So I'll say lock.acquire. Okay, and only one thread or process can acquire a lock at a time. There are other types of locks that allow you to have multiple, but this one is very specific in that it only lets you get one at a time. And I'll say lock acquired in a debug statement. And then just for safety reasons, I want to make sure I could never exit this method without releasing that lock, because otherwise I could lock all the other threads and they will never be happy. Okay? So I'll put this guy back out here. No, you need to be here. And how can I prevent it from happening? I can add a finally here and make sure that the lock is released by saying release. And then I'll just say lock released. Okay? And then what happens inside is all the same. The biggest difference is now it'll stay here on the lock acquire statement as long as it takes to acquire the lock. Only one process gets the lock at any time. Once it's acquired, everything that happens inside this code until the release statement is protected, as long as there's something else that's obeying the lock. There's nothing to stop another process from monkeying with L. Okay? It's not like L is magically protected now because of this. We're entering into a contract saying anytime you want to work with L, make sure you acquire a lock first. That's really what's going on here. So once we get the lock, everything will happen atomically. In other words, as one operation. And then you release the lock and everything's set to go on its merry way. Let's make sure this is the right call. We're setting the lock. And now we should be able to test it. I'm going to turn off the no lock code and I'll run this again. So you can see the lock gets acquired, released, acquired, released, acquired, released. And then when all the workers are done, we will finally, hopefully, see the Fibonacci sequence. We're almost done. We're in the worker 7, 8, 9, and then there it is. And we do have 1, 2, 3, 5, 8, 13, 21, 34, 55. And this is, in fact, unless I'm mistaken, the Fibonacci sequence for the first 12 numbers. Now you may have noticed that it actually took a little longer to run, and that's because once we acquired the lock inside of this process, it essentially stopped all of the other processes from doing any work. Now, if the sleep happened before we acquired the lock, it'll be plenty fast. As a matter of fact, if we get rid of this sleep, the code will still behave the way it's supposed to. And you know what? I don't really need to see the start and stop of these anymore, or the start and end. I think that's actually just noise. You can see they all 0, lock, released. It's acquired, released. 1, 2, 3. And notice here 5 gets in before 4. But notice 5 is together, 4 is together, 6 is together, 7, and 8. They're all together. So even though the processes happened out of order, they were still atomic in the sense that they worked to get the lock acquired and released as one group of statements before any other worker could also acquire and release. And we still get the Fibonacci sequence. So as you can see here, it's not dependent on the order. So the fact that 4 came after 5 did not affect our results. What would have affected our results is if we did not do the lock, we could not guarantee we would always get this sequence of numbers. It just really depends on how fast these statements would operate with each other. So locking is extremely important anytime you're sharing memory. This is one of the simplest synchronization techniques. There are other types of locks out there like reader-writer locks, which allow you to do multiple reads from a given data source, but only allows a write to happen in an atomic manner like this. So anything else would have to wait until the write is completed. But if you have 5 different threads or processes wanting to read the value, they could all read at the same time. But as soon as a write happens, everybody else is stopped until the write is completed. So that's another form of locking. So synchronization is something, especially with threads, you want to watch out for, because if you do share memory, something like this, unless you have very atomic operations, which there are very few, you will end up possibly getting corrupted data and definitely not the results you may be looking for.